Okay. So first point, he said coordination compounds, like in these sort of compounds, in coordination compounds, metals show two different types of linkages. So they show two types of linkages. So one corresponding to the primary valency and the other one corresponding to the secondary valency. So this is what we discussed, like one being ionic and the other being the coordination bond thing, the covalent. Yeah. Then what else did he say? The primary, like whatever is bound by the primary valency, whatever is ionic in nature is ionizable and is satisfied, like the primary valency is satisfied by negative ions. And the secondary valency, this is non-ionizable. So whatever is bound by the secondary valency, you cannot break them down into ions. And this is also satisfied by, like this can be satisfied by the negative ions or neutral atoms. Okay. So this particular secondary valency, is also called its coordination number. Next, last point, the ions or groups bound by the secondary linkages or secondary valency they have, like just like how in the case of covalent compounds we said that depending on how the bonds are arranged, they have a specific spatial arrangement, right? Tetrahedral, octahedral, bent shape, trigonal, bipyramidal. That way, even in coordination compounds, depending on the coordination number, like depending on how many bonds they are bound by, there's like a specific shape to that particular molecular species. So that's what this point says. So ions or groups bound by secondary linkages, they have a characteristic spatial arrangement. So that is corresponding to their coordination number. Yeah. So these particular spatial arrangements are in the form of different polyhedra. Like to say it simply, there can be either tetrahedral, which is like 4 bonds, or they can be octahedral if there are like 6, if the coordination number is 6. So the spatial arrangements are polyhedra. To summarize these points, tetrahedron or octahedron. Polyhedra is just like a general name for like how you call polygons. So quadrilaterals, squares, rectangles, pentagons, hexagons, all of them together you call them polygons, right? That way polyhedra, tetrahedron, octahedron, all these different 3D structures, you call them as polyhedra. So general notation of any a coordinate compound is represented by square brackets, metal atom, and whatever anions or neutral atoms. So whatever is satisfied by the secondary valency, the coordination number is inside the square brackets, and whatever is satisfied outside the whatever satisfies the primary valency, whatever is ionizable, that is given outside the square bracket. Okay? Like visually, you can think of it as you have a metal atom. So सबसे पहले, because these are directly sharing the electrons with the metal atom, you have like A, and this overall will have some sort of a charge, right? Either positive or negative charge. In this case, positive charge. And these positive charges are satisfied by the negative B atoms. So जो भी so this is the coordinate complex. That's what we call it as. So whatever is inside the coordinate complex joined by coordinate bonds, and that's non-ionizable. Whatever is outside can get out easily. So this is quite ionizable. You can think of it that way. This is obviously not an accurate figure. It's just, yeah, just to have an understanding. Metal atom M is in the center. So यहाँ पे A represents the coordination entities. And B represents, they are also called counter ions, because they are countering the charge that this particular ion would have. Suppose M is also neutral, A is also all neutral, then there won't be any counter ions in that case. Usually, of course, we're going to go deeper into this, but generally, if the coordination number, remember, coordination number we've defined as number of bonds that a particular coordinate compound has. So if the coordination number is equal to 4, you end up having a tetrahedron. This is similar to if you have 4 covalent bonds, you get a tetrahedral structure. Same rules apply. So for example, cobalt CO, NH, the platinum one, so PT, Cl4, Cl4. So in this case, platinum is linked to 4 chloride ions, right? So square bracket के अंदर जो है, that is the coordinate complex. So you look at how many species or how many bonds the metal atom has. In this case, platinum is connected to 4 chlorine atoms. In this case, chloride atoms. So इसलिए the coordination number is 4, and that's why this particular complex will have a tetrahedral shape. A tetrahedral structure. Okay.
Ma'am, but what if there are 5 of them?
If there are 5 of them, can you tell me what shape it will take up?
Trigonal bipyramid.
Yeah, trigonal bipyramid.
So in 4 wala, we don't have square planar.
Sorry, can you repeat that?
Like you said, Cl4 is there, then we have tetrahedral. So we don't have square planar.
Yeah, my bad. So nickel cobalt, this is tetrahedral. Platinum wala complex takes up a square planar. So it depends on how many electrons are there and the electronic structure and all. I got confused. So nickel, like this nickel with 4 cobalt, it's linked to 4 cobalt, so that's a tetrahedral structure. Another example, if you have like the platinum one, PtCl4 2 minus. यहाँ पे भी coordination number is 4, but in this case it takes a square planar structure. So whether it takes tetrahedral or square planar, that depends on what is the like what orbitals are taking part in bonding. Like if it is sp3, it'll go with tetrahedral, but if it is like psp2, then it undergoes like then it ends up with a square planar. So that you have to get into the electronic configuration and see what. But as a rough thing, if the coordination number is 4, you either get tetrahedral or square planar. And if the coordination number is 6, like in the case of the ammonia wala thing we saw earlier, CONH3 taken 6 times 3 plus. In this case, you end up with octahedral structure. Another point we need to discuss about, once you've noted down the compounds examples, we'll go to the next part. So apart from this, usually in organic chemistry, you'll also come across something called double salts. Have you guys come across double salts before? Like, have you heard of this before? Okay. So double salts, like in inorganic chemistry, whenever you have like a compound, whenever you have an ionic compound forming from a cation and an anion, we call that a salt. That's why whenever acid and a base react, we always call it salt plus water. So suppose you come across a random stone or a mineral or a compound, जिसमें you have 2 cations and 2 different anions. Now it's like 2 different salts existing in the same structure, same ionic crystal structure. So that sort of a case, that sort of a situation is called a double salt. Okay. So for example, like this, obviously, if you're doing it in the laboratory, under specific cases, double salts will be formed. But otherwise, when you're just doing an acid-base reaction, you'll always get a regular old normal single salt or simple salt. But this you'll come across it whenever you're mining for ores, minerals, where there's like many different types of compounds that are present in them. So as an example, carbonylite is an ore, it's a mineral of like this is a mineral that consists of KCl as well as MgCl2, and of course you have some water of crystallization. Now in this case, carbonylite is made of 2 different salts, all of them existing in the same crystal structure. You have potassium ions, magnesium ions, and chloride ions all present in the same structure. So when you mix this in water, all of them are going to ionize. You get potassium ions also, magnesium ions also, and chloride ions also. In this particular case, 3 chloride ions. Okay. Now, because you have 2 different compounds present in the same crystal structure, carbonylite comes under a double salt. Okay. Another example of a double salt, like this is usually used in chemistry for tests and reactions and all. It's called Morse salt. So this one is made up of iron and ammonia.
This is FAS, na? FAS we call it now commonly.
That I'm not aware of.
Like ferrous ammonium sulfate.
Sulfate makes sense. Yes.
We
Does it
did it in
have?
practicals.
Oh, you did.
Yes, titration of FAS.
Ah. So that's a double salt because you have two different salts there. You have ferrous sulfate also and ammonium sulfate also. And how many order of crystallization? This has 6H2. Okay. So in this case also, if you do the salt analysis, this is going to test for iron ions and ammonium ions and sulfate ions. It's going to give positive results for all three of them. Okay. So double salts are, so like one basic difference between double salts and coordinate complexes or coordinate compounds is that double salts are capable of dissociating into ions completely. Now this does not happen with coordinate compounds. Complex compounds does not dissociate completely. So for example, iron ka hi, suppose we have FeCN taken 6 times 4 minus. Now this is not going to dissociate into iron ions and cyanide ions because it is like, yeah, it's under a complex bond. Like if we neutralize this with potassium cations, this is not going to give me K plus. This will give me K plus, yes, but this part is not. So this part will not happen because it is inside the coordinate compound. This part will happen. So instead, this is going to dissociate into K plus and the complex anion FeCN6 4 minus. So that's an important distinction between double salts and complex salts. Double salts, maybe you may have like 2 cations, but both of them are in ionic bond with the anions, which is not the case with coordinate compounds. There's no ionic bond between one of the metal atoms and the anion. This is a coordinate bond. Okay. All right. Now this is like your basic introduction to coordinate complexes, coordinate coordinate compounds, complex compounds also called. Okay. So some terms that we'll be using with this is coordination entity. So like I'm just gonna write down like a basic what does a coordinate compound look like. Suppose we have metal atom and any random A taken X times, and then you have By. So coordination entity is the central atom, which is M in this case, the metal atom, or ion, which is bonded to a fixed number of ions or molecules. Okay. So this particular part is called the coordination entity, like the part which is bonded to the fixed number of atoms and ions, atoms or molecules or ions. So this particular part, metal atom, this is the central atom, is the coordination entity. Yeah, so the atom or ion, this particular M, so this whole thing is a coordination entity. Out of this M is the central atom. So you call it central atom or central ion, depending on what its charge is. अगर उसका charge 0 है, then it's called a central atom. If it has a specific charge, then it's called a central ion, because it's like at the center of everything. ठीक है. An important thing about central atoms or central ions is because they are accepting electrons from the anions or neutral molecules, they are said to be Lewis acids. So they act as a Lewis acids because they are electron acceptors. Because they are accepting electrons from the anions or molecules. Next one, this is very, very important. From now onwards, we'll be using this word only, ligands. So every time I say anions or neutral molecules or electron-rich species, the thing that is bonded to the central atom, we call them ligands. So ligands are ions or molecules that are bound to the central atom or ion. So ligands, they can be the many different types of ligands that we come across. They can be a simple ion like Cl minus. They can be small molecules like ammonia, water, these sort of thing, even carbon monoxide. And this is not like restricted only to Cl minus, they can be like bromide ions also. We come across many different ions. They can be large molecules. So one of the large, like a lot of these large molecules that are bound tends to be organic molecules, like ethylene diamine, which is shortened to EN usually. So we'll come across the nomenclature part also later. So ethylene diamine ka structure is H2N, CH2, CH2, NH2. So these sort of cases, whenever you have a large molecule that is bound, there's a possibility that यहाँ पे दो nitrogen है, both these nitrogens can get bonded to the central atom or ion. So we'll look at those sort of cases. There's a special term used for that. We'll come across that. They can be macromolecules. This is what we find in the case of organic structures. Mainly proteins. This is what is happening in the case of hemoglobin, chlorophyll, all these structures, vitamin B12. The thing, that whole thing surrounding it is a big protein. It's not like one specific molecule. So it can be anything as long as it has electrons to give, and it has electrons to give in the right place. Like if it's a really long chain, but if it's not like curving around, then it like, as long as there's electrons to give, it is a ligand. As long as it is donating a pair of electrons, whether it is an anion or a neutral molecule, whichever size of molecule, it will be a ligand. These are the different things. So in this case, yeah, so we defined M as the central atom. So apart from that, this particular A part of it, the thing that is giving the electrons, is the ligand. And this whole bit, which is in square brackets, is the coordination entity. Okay. That's the whole thing. Now, there are different types of ligands depending on how they are bonding with the central atom. Okay. Sanskriti, let me know when you're done. Then we look at the different types of ligands.
Ma'am, I'm done.
So you have unidentate ligands. Can you take a random guess what unidentate ligands could mean? Like uni agar hai, to what does that stand for?
One bond with the center.
Yeah. So if it is bound by a single donor atom. Donor atom matlab the atom that is donating electrons. Okay. So if there's only one bond with that whole structure, if it's bonded only to one of the atoms in that particular molecule ion jo bhi hai, that's a unidentate ligand. Similarly, you have didentate ligand. So didentate is when it is bound by two donor atoms. So example for didentate is ethylene diamine, like bigger molecule that we saw. So ethylene diamine, you have CH2, CH2. Now both of these are bonded to, like you have two amine groups, right? NH2, NH2. So didentate ke case mein, this nitrogen has one lone pair of electrons, this nitrogen has one lone pair of electrons. Now both of them will form a coordinate bond with a single metal atom. So because एक ही ligand के साथ दो bonds form हो रहा है, so this comes under a didentate ligand. So there are more like species also. When we come across a list of ligands, we'll look at each one of them. But yeah, didentate, how two donor atoms का मतलब single ligand which is ethylene diamine, उसमें दो atoms है. There are two different nitrogen atoms that are capable of donating electrons. That's why that's a didentate. And if there's like more, you can talk about tridentate, polydentate, like tetradentate, but all of these you can generalize them as polydentate. Just like we have monomial, binomial, trinomial, polynomial beside. Polydentate ligands are when you have many donor atoms. When we say many, they can be 2, they can be 3, they can be 4, 5, can be anywhere.
Ma'am, any example of 3 or 4?
There's one for hexadentate. So you have CH2, CH2. Again, this is also organic. N, N, acetate. CH2, COO minus. The really big molecule. So this is a polydentate ligand. Specifically, you have the lone pair on nitrogen and 4 acetate. Like I'm gonna highlight them with a different color. So you have the lone pair on nitrogen, and you have each of these acetate structures. So there's 6 different places where a metal atom can bond. So this is a hexadentate ligand. To give more examples, unidentate में chloride ion, H2O जिसमें only oxygen has lone pair of electrons, ammonia which has single thing. So all of these are unidentate. Even carbon monoxide is unidentate. So didentate में you have ethylene diamine. Even oxalic acid comes under didentate.
Ma'am, what is the name of the hexadentate ligand?
Um, so it is shortened to EDTA. Uska full form.
Oh, we have done this in school. That's why I thought I've seen this.
Yeah. So I mean, if I look at it, ethylene diamine tetraacetate, I think. Let me.
Yes.
Yeah, ethylene diamine tetraacetate. Ethylene diamine tetraacetate. You can figure it out. You have 2 carbon atoms, so ethylene. 2 nitrogen, say you'll get a diamine. And there's 4 acetate groups, so you have tetraacetate. So what are its what are the specific atoms that bound to the central atom? It has 2 nitrogen atoms plus 4 oxygen atoms that connect to the central atom. Now, from this, we get another term, like a special case, whenever you have a didentate or polydentate. Like this example may, you kind of see a loopy structure, right? It's maybe you'll have a loop, like if you have the same metal atom being bonded to nitrogen and the acetate molecules, it's kind of like a bridge. Can I call it a bridge? No. So it's like a loopy kind of a structure. You get ring structures. So that phenomenon is called chelation. And we say that didentate and polydentate form chelated structures. So didentate and polydentate, these two we say they form chelates or chelate ligands. So what is chelation is basically forming a ring structure when you have multiple donor atoms within the same molecule, which is bonding to the central atom. So whenever you have like a ring structure being formed in the coordinate compound, you call that a chelate. This process, this phenomenon is called chelation. Chelation, chelation. And those specific structures are called chelates, chelated structures. These ligands are called chelate ligands. So why do we have a special term for this? Is chelated complexes are more stable than unidentate ligands. Okay. So because there's sort of a symmetry being formed, and then the metal atom is being held from multiple sides, right? So if the coordination number is 4, it's kind of balanced in its structure that way. So chelated complexes are good, they're important, it's good to have them, and they are more stable than unidentate ligands. Okay, rest of it is pretty simple. So ligands is the important thing. And from now onwards, I'll be referring to all of this as, like, every time I talk about ligands, then you should know that it's the negative atom or the neutral atom that's bonded to it. From now onwards, be talking about ligands only. And is say, yeah, talking about like unidentate, dentate, tridentate, polydentate. This also gives us something called denticity. So denticity is the number of ligating groups that a particular compound has is called its denticity. Ligating groups matlab how many groups are uh, able to act as a ligand to a central atom. Like अगर didentate है मतलब इसका denticity is 2 because it has 2 donor atoms. Hexadentate है मतलब इसका denticity is 6 because there's 6 atoms that are capable of donating electrons. Okay. So that's denticity. So based on the denticity, you have unidentate, didentate, polydentate. Agar di, poly, like if there's more than one, it kind of forms a ring structure. So that's called a chelate or a chelate ligand. And that phenomenon, that process is called chelation, like forming that ring structure. And the special thing about a chelated complex is that it is more stable than a unidentate complex. That's the important. Okay, what else? Huh. And finally, last type of ligand we have is ambidentate. Can you figure out what could be an ambidentate ligand?